All right, time to get started. I'm sure you're all diligently discussing assignment 1. Remember that I do have office hours today. I expect to see a few of you for assignment 1. I would recommend to come today for assignment 1. As soon as I get back to my office from class, assignment hours will be then until 5. I know it says 4 to 5, but if I get back at 3:30, then I'll have it 3:30 to 5. So please come by today. I extended the assignment due date to Thursday, but we're giving out assignment 2 today. So assignment 2 will be available for download later this evening by midnight, and assignment 2 or assignment 1 will be due on Thursday. They overlap a little bit, but some people had some circumstances where they needed an extension, so I just gave it to the whole class instead. There's a lot of stuff to go over for assignment 2, so I'm just going to jump right into it. Okay, so assignment number 2, we're talking about the A-star search algorithm and some grid pathfinding optimizations. So what's new in assignment 2? We have the A-star search algorithm. We have multiple object sizes. So in assignment 1, it was just occupying one cell in the grid. Now it can be multiple different sizes. We're going to have 4 and 8 directional movement. We're going to have heuristic functions. We're going to talk about connected sectors, what they mean, and some other pre-computing and optimization. So things to make assignment 2 run a lot faster than your assignment 1. Here is the algorithm that we're going to be implementing. So this is A-star graph search, meaning A-star with a closed list. And so you've all seen this before. It's essentially just the standard graph search with a closed list, except A-star, you're removing the minimum F value from the open list. So you're going to implement the open list with either a straight array or using the data structure that I've included for you, and you're going to be picking the minimum F value. The rest of the algorithm is exactly the same. But if you want, here's the exact pseudocode for assignment 2. So this is kind of a solution for assignment 1, but not really. There are extra things in here, so you can't put all of this into assignment 1, but this is the danger of overlapping assignments. The slides are released. You don't need to take pictures. Just look at the PDF. It'll be there. I'm not like just giving out this stuff here. Also, the node class has some new variables, so it still has x, y, which is the state of the node, the action, and the parent, but now it also has g, which is the g cost, which is how far it's come so far, and h, which is the heuristic function, of which we will have several different types, which we'll talk about in a second. And just keep in mind that the child's g cost is equal to the parent's g cost plus the cost of the action. Hopefully that should be pretty intuitive by now. So if I'm right here, if I've come like 1,000 to get right here, and then I go 100, then the g cost of right here is 1,000 plus 100. Okay, so that's how you calculate the g cost of a given node. Just like before, we're going to be working within the same environment. However, with diagonal moves come new actions, new costs, and new action legality. So we're going to do a whole bunch of stuff about this. In fact, the easiest part about assignment 2 is the A-star algorithm. So there's lots more stuff to do here. So we have our grid, x 0, 0 is up here, x increases to the right, and y increases going down. So this is the same as the assignment, except now, instead of just up, down, left, and right actions, now we have up left, down right, and down left. And their corresponding x and y changes. So again, x increases right, y increases down. So moving down right is 1, 1. So a change of 1 in both the x and the y. And let's say top left is going to the left, which is -1 in x, and -1 in y to go up. So that's how your actions are given here. The action costs have changed. So in assignment 1, all of your action costs were 100, so it's just moving a distance of 1 times 100. And here I've got an action cost of a diagonal of 141, and I think I went over this before, but essentially this is just the square root of 2. So it's a Pythagorean triangle, as a right triangle, you use Pythagoras, so it's 1 plus 1, which is 2, take the square root of that to get the distance of a diagonal move. So that's 1.41 blah, blah, blah. And I just round it off to an integer. So we're only working with integers in the assignment. This makes it easier for the slides, and it makes it easier for your sanity when you're trying to check things in the assignment. So it's an approximation of the distance traveled by a diagonal move. All right, legal actions. We get the basic stuff, like an object can only occupy a region if all the tiles underneath are the same color. So this was not a factor in assignment 1. In assignment 1, we just had a 1 by 1, so exactly one cell of the grid was occupied by the object. So you could place an object anywhere in the grid, right? There was no place in the grid that you could not place an object. But now, and I'll have an illustrated example of this, if an object is greater than size 1, it will occupy multiple tiles or multiple cells, and all of those cells have to have the same color in order for it to be legally placed there. An object can only move to a space if all of the new region is also the same color. So when you're moving, there are multiple tiles to check. Okay, and I'll have another example of that. An object must be entirely within the map, and so you can't go below 0 in x or y, but also you can't have an object be on the very corner of the map if it is of size greater than 1, because then only part of it would be within the map. And this is the biggest change, which I will talk about in depth, is that a diagonal move cannot allow the object to jump over a tile of another color. And I'll illustrate that in a second. But this is the action legality that is new for assignment 2. One, these three are because of the size difference, and this one is because of diagonal movements. So let's have a look at object sizes. So before, we just had an object of size 1 in assignment 1, and so size really wasn't an issue at all. In this assignment, we will have objects of size 1, 2, and 3. And the location that I give you for an object, so the state of an object, refers to the upper left tile of that object. Okay? So if it's size 1, 2, or 3, these are all in the same location. So again, the state that I give you is the top left cell of the object. And we have this new notion of whether or not an object can fit somewhere. With 1 by 1, that wasn't a problem. So this object right here, its state is at the top left corner, and it is of size 3 by 3. And the object can fit because all of the cells underneath it are all blue, right? So you take this tile, and you check it against all the other 8 tiles, and if they're all the same color, then it is a legal place to put that object. This cannot fit. And the reason it cannot fit is because some of the tiles are a different color than other tiles. And so you can imagine the for loop you'll have to write in order to check this. So you would start at your given location, you would loop over x for the amount of size, and then y for the amount of size, and so it's a for loop and another for loop, and you would just check to see if they're all the same as the original tile. So it's not too hard. Legal actions are different, and this may be the biggest difference in the entire assignment in terms of things that have changed. So right here, we have an agent living at that state, and before we could only move up, down, left, and right. And so our object legality, or our action legality, was pretty easy. All we had to say before was, is the destination tile the same color as the source tile, right? And so we could move up, we could move right, we could move down, but we cannot move to the left. So that condition still holds for assignment 2. You can't move to a different color, but we also have this additional thing of you cannot jump over or slide over tiles. So what does that mean? Well, I'll attempt to draw something here because I think this is the best way to do it. So we can move up, we can move upright, we can move right, we can move down right, we can move down. So true means we can move from this x to there. F means false, we cannot move there. So This down left, that's pretty obvious. It's not the same color, so it's not legal. To the left, well, that's not the same color, so that's not legal. But this one, that one's a little bit strange. Why can't I move from here to here? My analogy is picture this was like a game of Scrabble, right? Where you've got physical tiles on a board. And you've got to slide this tile from here to there. If it touches any tiles of a different color, then it's not a legal action. So what we can do here is if I draw this, if I draw the movement, so I'm using a trackpad, apologies. If I draw the corners, so this corner moving to there and this corner moving to there, if either of those touch a different one, then it's not a legal action. Okay? And similarly, and I've got a proof at the end of this that shows an interesting equality here that will simplify things for you. But intuitively, picture you have to physically slide a tile diagonally, and if it would touch any other colors, then it's not legal. So let's look at one more example of an object of size 2 by 2. So you can move to the left. That's pretty easy. You can move down and to the left, and you can move down. All right. We cannot move down and to the right because one of these tiles, and specifically this tile here, would slide over that green tile. So that is not a legal action. We can't move to the right because this tile would be overlapping with that tile. And apologies to anyone watching the video, you can't see the laser pointer. Let me go back and do this with the virtual laser pointer. Hey, look at that. Okay, so we can move to the left because nothing is blocking it. We can move down and to the left. We can move down. However, we can't move down right because this tile right here would slide over this green tile right here. We cannot move to the right because it's a size 2 by 2, so this tile would be overlapping that tile. We can't move up and to the right because most of the object would be on a different color, so that one's obvious. And we can't move up because this tile would be overlapping a different color. And we can't move up and to the left because, again, if I were to draw this, so I'm going to draw from here to here, and I'll draw from here to here to move up and to the left. Then if I have that, you can see that this tile over here would indeed slide over that one. So you just can't slide over tiles when moving diagonally. That's the rule. Okay, so if we have this situation then, this tile down here, in order to get from this starting location, so the top left is the start location, but it has size 2 by 2. In order to get from here to here, we cannot go up this diagonal because we would be sliding over the green tiles. So in order to get here, we would have to go all the way around up to here. Let's look at one more example. In this example, we actually can move this object through this area right here, but we cannot do it via diagonal actions. We can only do it via up, right, up, right, up, right. Why? Because if I tried to move diagonally, well, this tile would be okay, but this tile down here would be sliding over to the right. So that would be, in order to get from the start to the goal, we'd have to move up, right, up, right, up, right, up. So that's how we would get there. Here's an interesting fact. What is the interesting fact I'm about to tell you? Okay, so if we look at the diagonal actions only, right here, so this one is not possible. This one is not possible. So that means moving from here to here, moving from here to here, moving down and moving up. Look at this. Here are the cardinal action legalities. So you may be asking yourself, how in the hell am I going to tell if something is sliding over a different color in my code? That's very difficult. It turns out that a diagonal action is only legal if its surrounding cardinal actions are both legal. So we can use that fact to help us with our action legality check. So look at this. If we have a false and a true, we know that this one is going to be false. If we have two trues, we know that this one is going to be true. We have two trues, so this one is true, we have true, false, so that one is false. And obviously, false, false would be false, right? So that is an interesting fact. So this means that upright is legal because upright and right up are both legal. So you can use that to help you. And down left is not legal, down here, because left then down is not legal. So for every diagonal action, we can think of the two cardinal actions that you would do to simulate that diagonal action. So for example, going upright, you could either get there by going up then right or right then up. And what this no jumping over rule means is that both of those different paths, up then right and right then up, they both have to be legal in order for the diagonal action to be legal. So if we look here, moving diagonally upright, that is not legal because right then up is not legal. So moving right is not legal, so any diagonal involving right is not legal. Okay, and if this isn't obvious like right away, it will be once you start playing with it, I promise you. Let's talk about paths. So let's say now that we want to look at a legal path from a start to a goal using these diagonal actions where you're not allowed to jump over tiles of a different color. Well, if down here is my starting tile, and up here is my goal tile, you might think that that is the shortest path. But that is not a legal path, because these diagonal actions are jumping over a green tile. Okay? So that is not the shortest path in this case. In fact, this is the shortest path in that case. So you have to go to the point where a diagonal action would not jump over anything of the same color. All right. And because of this equality here, because of this fact, it actually makes the assignment easier. So if this was not the case, it's actually easier and faster to compute actions. Maybe not faster, but at least as fast, because we can compute these orthogonal actions, and from the orthogonal actions, we have the legality of the diagonal actions. So even though it seems more complicated, because it is a little bit more complicated to understand, computationally, it's not that much more expensive, if at all. And the path cost changes a little bit. So in assignment 1, we had the nice property that in assignment 1, all of our actions had cost 100. So to find the cost of the path that we produced, we could just take the length of the path, the number of actions, and multiply it by 100. But we can no longer do that. Okay? We actually have to compute the length of the path. And it turns out that as we generate the search tree, we are storing G. And so once we pop the goal node off of the open list, it will have a G value, and that's the cost. So we don't need to actually go through all the pointers and take the actions and then figure it out after the path has been created, because the goal node will contain the length of the path, which is the G value. Okay. Another thing that's new are these heuristic functions. So A star is f of n equals g of n plus h of n. So we talked about g, now we have to talk about h. And remember that h is our heuristic, h for heuristic. That is the guess at how much distance we have remaining from the state of a given node to the state that's the goal state. So in assignment 2, I will have a function. It's called estimate cost. And that estimate cost function takes in a current x and y and a goal x and y, and it guesses at how much distance you have remaining. And you will be implementing 4 different heuristic functions. Now, you say 4 functions, holy crap, that's a lot of work. They're all kind of the same function, right? It's really not that much work. So the first one is going to be called dist. So the way, remember in assignment 1, when you had the config, or have, I guess, it's still current. So you have this.config, and you can say this.config. What is it? Method equals BFS. What did I call it? Strategy. So there was a this.config.strategy. Here, you'll have a this.config.heuristic or eval or something like that. And so based on one of these strings, you will compute the different heuristic. So dist, that is just the Euclidean 2D formula. So that's just Pythagoras, so the square root of the sum of the squares of the x's and the y's, or the differences in the x's and the y's, just the distance formula. Card, that is the cardinal Manhattan, or 4-directional guess. Diag, that is the diagonal, or 8-directional Manhattan distance. And 0 is return 0, literally. And the reason I include the return 0 heuristic is because what you can do is implement your algorithm and then test your algorithm with the 0 heuristic. So if you test your A-star algorithm and you're not getting optimal paths with your heuristic, maybe that's because you did the algorithm wrong, or maybe that's because you did the heuristic wrong. But if you have a 0 heuristic, that's guaranteed to be admissible, right? It's guaranteed to be to work for A-star. So if you just use the 0 heuristic and you're still not getting optimal paths, then you know that the problem is with your algorithm and not with your heuristic. So test your algorithm with the 0 heuristic. Once it works with that, then test it with the other heuristics. And so for your heuristic function, you will be given an x and a y. That is the starting, not the start state of the problem, but like the state at which you want to guess from. So my example that I used from before, the xy would be me here, and the goal x and goal y might be that garbage can over there. Here is the Euclidean distance. So you would take those x's and y's and just return the result of the distance formula based on those. So that's probably the easiest one. For the heuristic function of the Manhattan distance, or the 4-directional Manhattan distance, that is the difference in the x's plus the difference in the y's. See that? So to get the length of this L-shaped pattern here, it's the difference in the x's plus the difference in the y's. And the absolute value of that, of course. You don't want to add negatives. The diagonal Manhattan distance is the trickier one of the two, but there's a cute little formula that you can use where you take the difference in the x's, then you take the difference in the y's, and the minimum of those two differences is how many diagonal movements you have, and then you add the remaining difference in the longer direction. Okay? So you see here, if I take my dx, that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the x's are 11 apart. The y's are 1, 2, 3, 4 apart. So 4 is less than 11. So I've got 4 diagonal movements, and then 11 minus 4 cardinal movements. And so you can use that little trick to calculate the length of the Manhattan, the diagonal Manhattan distance. And the 0 heuristic is literally return 0. I've had people in the past, not too many, but they thought it was like a trick, that there was actually some calculation. No, it's actually just return 0. And what algorithm does A-star become with a heuristic of 0? Nope. Uniform cost search. Perfect. All right. So you get on the second try. Next new thing in assignment 2 is the idea of connected states. And this will answer the question of why didn't the solution turn all red if there was no path? So that's what I did for my solution. My solution for assignment 1 is actually the same as my solution for assignment 2. I just used it for assignment 1. So what is a connected state? Well, states are considered to be connected for an object of a given size if a legal path exists between them, no matter how long. Okay. Another little definition. A connected sector is the entire set of states that are all connected to each other. That's just a definition that I'm giving it, and I'll show you an example in a second. In assignment 2, holding down the right mouse button highlights all the states that are connected to the clicked state. And I'll give a demo once I'm finished with all the slides. So I'll give a demo of the assignment, and then I'll go into the code of the assignment. An important property is that connectivity, it's supposed to be is, connectivity is transitive. If A is connected to B, and B is connected to C, then A is connected to C. That's actually an important property. So if I'm at A and I can get to B, and I'm at B and I can get to C, it means that A must be able to get to C. Whether or not it has to go through B, that's not clear, but it can at least, we know it can get to C. Yep?
Are the connected sectors pre-computed at runtime?
We'll talk about that. I'm about to answer all that. Was that another question? No? Okay. So let's do an example of connectedness. What is connected here? Well, these two are connected, right? So let's talk about an object of size 1 first. This state up here is connected to that state there because a legal path exists between them. What about these? So for size 1, A, B, and C are all connected. I can obviously get from A to C, I can get from C to B, and I can get from A to B, right? So you can see now why if A is connected to C and C is connected to B, then by definition A is also connected to B. But you wouldn't necessarily take the shortest path by going from A to C to B. You could just go down, okay? These are not connected for objects of size 2 or 3. Can anyone put up their hand and tell me why all of these are not connected for objects of size 2?
For C, it wouldn't fit.
It wouldn't fit, right? So no path exists to C because we cannot put an object of size 3 or object of size anything greater than 1 at C. So that's a little kind of trick question there. No path exists because one of them is not legal. This is connected for size 2. Okay? So if I have an object living up here at C, I could go left and then down to get to A. I could go right, down, and left to get to B. And so they all are connected for size 2. However, they are not connected for size 3. Why are they not connected for size 3? Because I've only got a little pathway here of width 2. So I can't move my object to get from C to B, or from B to A, or from A to C. So for objects of size 3, they are not connected. So connectivity depends on the size. That's an important part about the assignment. Also, the trivial case, this state here is not connected to this state here because they're different colors, right? So that's a quick check. You can just see if they're different colors. So they are not connected, and they're very sad. All right. So in the assignment, if you hover over with the mouse on any tile and you right-click, so if I right-clicked on any of the tiles of that green, it will turn them all pink, meaning all of these pink tiles are connected to each other. Why pink? Because I just chose it as a color. It doesn't matter what the color is. So let's talk about how we would compute connectivity. I got a couple of questions about this for assignment 1, and I said, just wait for assignment 2. I promise we'll get to that. And so you may think, well, in order to tell if a path exists between two states, I'm going to have to compute the path. So is there any faster way to compute the connectivity other than just to compute all the paths? And it turns out that there is. So the first thing that we need to realize is that a diagonal move is only legal if both of the surrounding cardinal actions are also legal. So we really have to understand that. And what that means is any path which is doable with diagonal moves must also be doable without diagonal moves. Right? So what this means is cardinal connectivity is the same as diagonal connectivity. And that's going to afford us something cool. And it's also easier to compute. So let's look at cardinal connectivity, and let's use an algorithm that's like BFS. It is a breadth first search, but it is not the exact BFS algorithm that we've been looking at. So what we're going to do is I'm going to create a second data structure that's the same size as the map. And I'm going to give it all zeros. So it's all 0. And what a 0 means is essentially, after we've done the computation, if there's still a 0 somewhere, it means the object cannot fit here. And by the time we're done, this will be populated with integers. And the thing will be the integer, if one cell has a 1, for example, that means it is connected to all the other cells that also have a value of 1. So how does that algorithm work? Well, I'll go over it intuitively first with a visual example, and then I'll give you the pseudocode for the algorithm. So you can start anywhere, but let's just start in the top left. And we're going to choose a tile. We're going to apply a breadth first search, and then we're going to go to the next tile and do it again, and the next tile and do it again, and the next tile and do it again. So what we do is, when we choose a tile, I've chosen the top left tile up here, I give it a new number, just an increased number since the last one. Since all I have are zeros, I just go to 1. And so that's going to be called the sector number. So I assign a sector number to this place up here. Okay, easy so far. Then I do a breadth first search with 4 directional movement from that 1. And anytime I have a legal action, I just mark that new state with a 1 as well. So here's what happens. On the first iteration of that, I go from the top left out by 1, so they become 1s. Then out from those, they become 1s. And then out from those, they become 1s. And then eventually, everything that those could touch will become a 1. So then what I do is I just ran the BFS for this cell. Now I do it for this cell. But if it already has a non-zero number, I've already computed it for that cell. So I can skip it. Okay? So I go to the next one. And I keep going until I get to a cell that has a 0. And what a 0 means is that I have not done this yet for this cell. So I'll give this one the next number, which is a 2. And then I do a breadth first search out from that, marking everything that it could touch with a 2. Now I've reached the limit here. So I go to the next line. Okay, there's no zeros here. I go to the next line. Oh, I've reached another 0. I do the next thing. Here's a 3. I breadth first search out from there, marking everything with a 3. Now all of these 3s we know are connected. And then I keep going until I get to the next 0, and I do it from there. And eventually, I have given all of my cells in this grid an integer value. And the cool thing is, if I want to know if any 2 cells are connected, meaning that a path exists between them, all I have to do is look up the value. And if they're the same, then they're connected. So we've done this one pre-computation. And the cool thing about this pre-computation is that you may say, well, you've done a BFS for every point on the map. But the thing is, the BFS only touched each cell once because we skipped over everything that wasn't a 0. So the amortized time complexity of this is not x times y times BFS. It's just a single BFS. Amortized time complexity just means that there's some other factor to the time complexity. And this one means that we would skip over everything that wasn't already 0. So let's look at the pseudocode for that algorithm. Some people prefer the visual. Some people prefer the pseudocode. I actually like a combination of both. Okay?
Shouldn't the grid change if you use some other size?
Well, we'll get to that. I'm leading up to all that. Yep. I'll give an example of different sizes when we get there. So computing the connectivity, I have a function called compute sectors. So initially, I'm going to have sectors, and I have a grid data structure. A grid is just a 2D array, so just an array of arrays. It has x width, the x dimension is the same as the width of the map, and the y direction is the same as the height of the map. And then I give them all a value of 0. So this syntax here just means make me a grid, which is a 2D array of width times height size, and give them all a value of 0. So that initializes that initial array. And my initial sector number, which is the integer that we're going to be inserting into that grid, initially has a value of 0 as well. Then this loop here is going to start in the top left and move over. So this is checking the cells that we want to apply this BFS to. Then, if the sectors up here, if the sector number is not equal to 0, right? So if we've already done the BFS here, or my object cannot fit at that particular location, then continue, meaning skip this cell. So again, let me just go back to the grid. So it means that if I get to a particular location and it's already not a 0, or my object can't fit here, then I certainly don't want to do the BFS, so just skip to the next one. Okay? Then skip to the next one, then skip to the next one, then skip to the next one, if it's not a 0. If the sector number is 0 and we can fit there, it means we want to do a BFS. So inside here, we increase the sector number, so it just goes to the next number. Then we do this cardinal BFS, meaning we BFS in 4 directions, starting at x and y and assigning a sector number. And that's basically it. That's the entire algorithm. And then, later on, we'll have a function called isConnected. And this will get passed in x1, y1, so one location, and x2, y2, which is another location. And all we have to do to check to see if two things are connected after the sector computation has been done is check to see if the sector value at x1, y1 is equal to the sector value at x2, y2. So you're just checking to see if those two numbers are the same. And this cardinal BFS here, that is just the process of going outward from a particular cell, and if it's a legal action, up, down, left, or right, and that cell is not already given a value, then give it the value that I'm currently assigning. Okay, so that's just a standard BFS. So two tiles are connected if their pre-computed sector number is the same. Hopefully that's clear by now. If we have said that they're in the same sector, then that means that they are connected. We can use that fact as a pre-check to see if a path is possible before we try to compute it. So if the start and the goal are not connected, then why should we try and find a path, right? So in assignment 1, this is the answer to all of those questions. Why didn't the solution turn all red when no path was possible? It's because I had pre-computed the sector numbers. And if no path was possible, I instantaneously knew it, and I didn't have to do the entire search and then run out of things on the open list for that search. Now, getting back to your issue, what happens when we have bigger object sizes in this connectivity? Well, here we have a big old object of size 3. And just keep in mind that this x, the location of the object, is not the middle, it's the top left. That's very important. So this represents xy for this object of size 3 by 3. As we move from here to here, for example, this action is legal because all of the new area that it will be taking up is the same color. However, this is not legal. And just keep in mind that going from here to here, it's represented by the top left. Okay. Now let's look at this. And directly the answer to your question is that for this particular environment, the object of size 3 by 3 can only live in these locations, right? It won't fit anywhere else because it's too big, because it will be overlapping multiple colors. So all of these values of x, that's where it could possibly live. So for an object of size 3 by 3, this will actually end up with a 0 everywhere else. Okay? Was there a question there? Okay. So if we do the same computation, we start up in the top left for 3 by 3, and we start filling it out. We go like this, like this. Okay, so here is the end. Where do I have? By the time we finish, this is what we have for an object of size 3 by 3. We can see that most of it is actually still 0. And that's because anywhere it's a 0, the object can't fit there. Anywhere it can fit does have a sector number, but for example, up here, this 4 is all alone. It's only connected to itself. Because an object of size 3 by 3 can't move anywhere here because it's sort of blocked in. Down here, this has a 3, and that's because all of these locations are connected. And just keep in mind that this 3 represents a 3 by 3 object living right with its top left right here. And in the middle, it's a little bit hard to see, but this is a 2, and this is a 2 because we could have a 3 by 3 object here, and it has one legal action of moving down. So, a little bit of an optimization, you may ask, is that once you have this computed, any time you want to know if an object can fit somewhere, you no longer have to check all 9 squares of the 3 by 3 object, because this will tell you if it's a 0, you can't fit here. So this is another example of optimization via pre-computation. So what we'll do is, once we initialize the environment, we do all of this pre-computation. Just once. And then it's useful for us throughout the entire search. So, speed optimizations. Keep in mind that the optimizations that I'm showing here, they don't affect the number of nodes that are expanded or generated. They just affect how long it takes to generate each node. So just picture, for example, this one. If I want to naively check if an object can fit somewhere, for an object of size 3 by 3, I've got to do 9 different if statements, right? Or I guess 8 different if statements. So for this 2, for example, I've got to check this 2 against this, and this. That's 8 if statements. But if I've already computed this once, then all I have to do is look that up and say, is it a 0? 1 if statement. So it's 8 times faster. But that doesn't help us theoretically with the time complexity of A star. It just helps us run hundreds of times faster, right? So time complexity people will say, you know, all that matters is the biggest exponent. The actual running time doesn't matter. Well, I will tell you that when you're trying to run an experiment and it takes 1 day versus 100 days, that does matter. When you double-click your program and it takes 15 seconds to run versus 30 milliseconds to run, that does matter. So constant factors matter even though they don't affect the theoretical performance of the algorithm. So none of these optimizations are required for getting the full assignment marks, but what I do for assignment 2 and going forward, every assignment will have a little bonus competition. And so for this class, the top 3 fastest running assignments will get a D2L trophy. There's trophies in D2L. Has anyone ever been in a class where D2L trophies were handed out? It's kind of amazing because only you can see them. But there's a print button and you can print out a little certificate if you ever want to put it on your resume, okay? I guess I'll announce it as well to the class. So for the people who end up caring about that, because I know, you know, most people are here just to get a piece of paper that says job please, like I get it. But for those of you who do care about becoming better programmers and want to make your code as fast as possible, the optimizations will take like 90% of the time of the assignment. So it's like, I'm doing the assignment, I've already got 100. Now it's time to spend 4 times that amount of time like doing all the optimizations. So, yeah. However, some of these optimizations may be required in order to get like full 60 frames per second operation of your of your thing, right? And if you're like making a video game in the future, you would want it to run fast. So like learn now instead of when you go apply for the job, then you'll know all these things. So let's talk about that connected sector optimization we just talked about. For larger object sizes, we may have some tiles that have a 0 value. This means that the object cannot fit. I've already said this. By pre-computing these values, we can use them later instead of doing the full object size check to see if all the underlying tiles have the actual same value. So for connected of size 3, a 0 means we can't fit. So I've already gone over that. Here's a legal action optimization, which is pretty cool. The rule of no jumping over diagonals gives us an interesting property. And I may have already jumped the gun and told you about this already. So a diagonal move of x, y, so that means up left, for example, is only legal if both x, y, and yx are legal as well. And this property holds for all object sizes. So, I just talked about this. So here, if we want to compute diagonal legal actions, all we need to do is compute the cardinal legal actions and then use the result of them to say, okay, is this legal? Well, if this is legal and this is legal, then that's legal. So it is. This one here, is this legal? Yes. This one, no. So that one's not. Similarly down here, and this one is legal because both of those are. So this is just a repetition of what I had before. Okay, these slides are literally duplicated. Another is legal action optimization. The most commonly called function in assignment 2 is probably the isLegalAction function, since it's called when every child node is generated. I guess canFit is called more, right? Because in order to know if an action is legal, you have to know if an object can fit. So canFit is called the most, then isLegalAction. We can use the pre-computed connectivity sectors to check for legal cardinal actions. Since actions are legal only if the source and destination tiles are connected. What does that mean? Well, let's have a look at this. Well, it means, say this is my connectivity for an object of size 3. If I'm right here up in the top left, and I want to know, is moving up a legal action? Well, I could do a whole bunch of calculation to figure that out, or I could just say, hey, it's the same number, so it is a legal action. Don't need to check sizes, don't need to check anything. I just need to check that they're the same number. Okay? That doesn't work on its own for diagonal actions. It only works for cardinal actions, because you would have to check if this one and this one are legal for the diagonal to be legal. So let's talk about that. So let's say we have 4 tiles, A, B, C, and D. Diagonal action of going from A to D is legal only if AB is legal, AC is legal, BD is legal, and CD is legal, right? So we would have to be able to go from A to B, then to D, and from A to C, then to D. So that's 4 checks. Are A and B the same? Are B and D the same? Are A and C the same? And are C and D the same? However, that just says that AB is legal if A and B are connected, so that's just a lookup. And AB, BD, AC, and CD are legal if each of A, B, C, and D are connected. So we can check if all of those things are all the same. If A, B, C, D is legal, then if A, B, C, and D are all connected, then A and D is legal. However, that's 4 if statements, right? To check those two, those two, those two, and those two. But because connectivity is transitive, if AB and BD are connected, then I know that AD is connected. So all I need to check is if AB, AC, and AD are connected. By transitivity, I have the 4th one, and so it's 3 checks to see if the diagonal action is legal. So all I have to do to check to see if a diagonal action is legal are those 3 connectivity lookups. And if you think about what you were probably thinking back at the start of this lecture, okay, how am I going to check to see if this diagonal action is legal with a huge object of a given size? Now I have to check all of the tiles up here, then check all the tiles down there, and then check all the tiles that we could possibly slide over and check those. No, it's just 3 lookups and really, really efficient. However, it's even more efficient if you want it to be. Think about it. Will legal actions ever change? Our environment is static, meaning tiles will have the same legal action for a given object size every time you visit. That means you can pre-compute all the legal actions for all the tiles. And later, just iterate over the list of legal actions rather than generating them each time, and this will result in a lot of time saved. What this means is, instead of checking all 8 directions and then asking if they're legal, we can generate all the legal actions for each state and store the list of all the legal actions and just iterate over those. What would that look like? Well, it would look like this. So up here, we would store an array at each grid cell. So I'd have another data structure that would have an array at each grid cell. I just saw like 5 people sigh. You don't have to do this if you don't want to. It'll make it a lot faster, but it's not part of the marks. But if you look up here, what's the legal actions up here? It's just moving down. You can't move up, left, right, diagonal. It's just moving down. So just store the fact that you can only move down there. Here, we can move up, we can move down, we can move right, and we can move down right. So store all of those there. And then whenever you're trying to generate the children of a node with that state, you can just look up the legal actions and iterate over those rather than looking at all 8 possible actions and asking if they're legal. Okay. The only thing I'm not allowing you to pre-compute in assignment 1, well, obviously all the possible paths, right? So don't do all the shortest possible paths, and I don't want you to pre-compute all the possible heuristics either, right? Because you could think, okay, if I have x times y, maybe I have 64 by 64, I could go through each tile and then iterate for that tile over all the other tiles and pre-compute the heuristic, but we're not going to go that far. I'm going to stop at the heuristic. Next, a closed list optimization. You can do this for assignment 1 if you want, but it is absolutely not necessary. Closed list stores unique states. So if we think of a closed list, right, we're just thinking of, is this thing in the closed list? So it wouldn't make sense for us to have more than one of a particular state in the closed list, right? So if state 2,3 is in the closed list, it doesn't matter if there's 1 in the closed list or 30 of them in the closed list. We just need to know, is it in the closed list? Meaning, has this state been expanded before? So each state on the map will either be in the closed list or not in the closed list. So this is like a different way of thinking about the closed list, right? The first way is I'm going to have an array, and I'm going to list out all the things that are in the closed list. The second way of thinking about it, in our assignment, which is a grid, and this only really works well in grids, is look at the grid. Each of those states is either going to be a yes or a no to whether or not it's in the closed list. So if I store, instead of an array of states, if I store a 2D array of trues and falses, that's the same size as the environment, then I'll essentially have a big lookup table that says whether or not something is in the closed list. And so if I use a little bit more memory, before what I had to do is take a closed list, which was an array, and look over all the values and check to see, are the x and the y the same? No. Are the x and the y the same? So that's a huge computation of checking to see if something's in the closed list. But just like the sector computation, if we build another data structure and use a little bit more memory, now checking to see if something's in the closed list is one lookup instead of having to iterate over a bunch of stuff. And so closed list membership insert and retrieval are both now constant time instead of linear time. For the open list, if you want to, what I would recommend is implementing the assignment with an open list as an array. And then when you want to go get the min value, just manually go through the array and find the minimum f. However, I've included a binary heap data structure in the assignment. Like I've included the code of it for you. And that is a priority queue. And so the binary heap, when you insert things into the binary heap, when you call pop, it will give you the minimum value based on the sorting function. So if you want to, and if you can figure it out on your own, you can use the binary heap. It will make things a little bit faster, but please, at first, implement it naively with an array and make sure it works. Test your algorithm, see if your A star works, before you use the binary heap. Because what can happen is, you implement it all with the binary heap at first, and it doesn't work, and you don't know if your algorithm is wrong or if you're using the binary heap incorrectly. So you always go through this with like an iterative approach. You do one function, test it, make sure it works. Now, okay, that's never going to be the source of error. Now the function that uses that function, you can write that function and test it and know that those two functions work. And in this assignment, there's like a function that uses a function that uses a function, right? So there's a real nice iterative way to implement all of this. Okay, do I want to keep? No, discard. Where is my mouse gone? I had this open. Okay, here we go. Oh my God. Okay, so this is assignment 2. Looks very similar to assignment 1. Let me just, and if you do the same thing, like the student code just gives you that same path, so it's not doing anything. Down here we have the solution A star. So this is what the solution looks like. Here we can change from a 1 by 1 to a 2 by 2 to a 3 by 3 square, and the paths are going to change based on that. I actually think that it's pretty it's weirdly satisfying to do this. Another example here is if I have a path from here to here, that's the fastest path. But if I change that to a 2 by 2, then that small path is no longer viable, so we have to move here. Here we can choose the legal actions, either 8 directions or 4 directions. And here we choose the heuristic function. So setting the value here, that gets passed into the config inside your assignment, and then you'll read from that config. Your tests run exactly the same. Run the tests. I don't know why that's wrong. It should be right. Let me just refresh. Oh, the reason that this is showing up as incorrect is because in this assignment, it truly runs the student code versus the solution code. In assignment 1, it ran the selected code versus the solution code. So this is running the student code here. So that's pretty much the same. There's nothing different about the user interface except this, which is when you hold down the right mouse button, it'll show you the connected sectors. So these are all the connected sectors. And you will notice that if I choose 3 by 3, it doesn't have some of them selected because the object of size 3 by 3 cannot fit there, right? And if I hold it down here, well, that's not connected to anything, so nothing shows up as pink. Okay, so that's the right mouse button. That's the functionality of the assignment. Everything else is the same. I don't need to show you anything else about that. But I do want to get into the code because I think I only have 15 minutes left by my clock. So let's get into the code. All right. This is awkward. I got to look at this monitor in order to do this. Okay. There's this binary heap data structure. I have stolen it from that location with credit and then modified it for this assignment. If you figure out how to use that, you can use it. It's not that difficult, but I've linked to it. Use that if you want. The grid class is the same as before. Nothing has changed. The GUI and the grid GUI, that's just the GUI. You don't need to worry about that. Nothing has changed about the HTML or the CSS other than the two new options. The solution code is literally the same file as last time. I'm going to be careful not to click on that one. And then I click on that one, and here we go. So I have included a step-by-step suggested method to solving this assignment because, trust me, I'm aware that there's a lot to do in this assignment. If you leave this till the last couple of days, you will not finish it. And if you ask for an extension, there's valid reasons to have an extension, but I'm also going to ask, show me what you've done so far. And if that is nothing, then you may not get an extension. So just make sure you're spending enough time on the assignment. This is, by far, the most work for an assignment in the class. Okay? So this is as hard as it gets in terms of the amount of effort. So the recommended order of completing this assignment, let's have a look. Let's make this bigger for you. 0. What I recommend is doing everything for size 1 only first. And then what you can do is come back and modify it to do all the sizes. Okay? That's what I recommend. Next thing to do, construct the function which computes whether or not a given size agent can fit in a given x and y. This will be used by compute sectors and isLegalAction. So what I'm telling you is the order in which to do the functions so that you're not doing anything until everything that it requires has already been done. So that function is down here. The constructor is exactly the same as before. So this is the canFit function. It takes in an x and a y and a size, and it returns, well, after you've computed it, whether or not an object can fit there. Okay? So you just fill in that. Check to see if the location of the top left is the same as all the other locations within that object. Later, if you choose to do the canFit optimization, you can change this code to use the pre-computed sectors that you've already computed. Okay, so that's step 1, the canFit function. Second, complete the compute sectors algorithm by using the 4-directional breadth-first search as shown in the class slides. Okay? So down here, this is the compute sectors function. That is where you will do that. And this function gets called inside the constructor of this object. So basically, in the user interface, whenever you select a different option, it will recall the constructor of this class. So whenever you select different options, it will reset the compute sectors. Did you have a question?
Yeah, this compute sectors, after completing it, can you tell us where should we call this function in order to...
So I just said, it's called automatically in the constructor of the object. So you never have to call that function. Yeah, and so just keep in mind that the computation of the sectors is done once for all sizes. So if you have an array, like let's say you do it just for size 1. So you would have this dot sectors x, y. But if you want to do it for all the sizes, now you might have this dot sectors x, y, s. So it may be a 3D array. Okay? I'll probably, if that ends up being a bunch of questions, I'll release some more help with that particular thing. So that compute sectors, after you finish it, every time a new options are selected, it automatically gets called for you. Okay. Use the results of step 2 to complete the isConnected function and then test it with the UI. So once you know that you can test if an object can fit somewhere and you have computed the sectors, then you do the next function, which is isConnected. And so isConnected, right now, by default, the student code if I come back here and reset this, the student code will just highlight everything that has the same color. Okay? And that's wrong. The reason for that is because the student code, by default, just checks the color. That's it. But what you have to do is once you've computed the sectors, here you using that function that I wrote in the slides, which is checking those different sectors to see if they're connected. Okay. Next, complete the isLegalAction function, which, if you choose to, can use the result of the pre-computed sectors for that. So down here in isLegalAction, that's where you'll write that function. It's pretty similar to assignment 1. Next, complete the start search function. That's pretty obvious. You've all done start search. The only real difference here is if you're using the binary heap, you'll have to reset the binary heap. Just reset all the data structures that you're going to be using at the start of a search. So the open list, the closed list, all that stuff you did on assignment 1. Next, do the getOpen and getClosed functions. So the only real trick here is that if you end up using the closed list optimization of having that map of Booleans, because it's much faster, what you will have to do is you still have to return the same array of states as assignment 1. So if you do use a different data structure for your closed list, you'll still have to go through and implement the getClosed function, which returns an array of states. And if you use the binary heap for the open list, you have to figure out how to iterate through that binary heap and return all the states that are in the nodes of that binary heap. So that's just the extra added thing of using the binary heap. Next, complete the search iteration function using A star with a heuristic of 0. So if we go down, so there's start search. Here is search iteration. You can copy a lot of the code that you wrote for assignment 1 in here, and the only real difference is that instead of doing BFS, instead of doing shift or pop, you're looking through the open list for the minimum F value. Okay, so that's the only real difference there. And then the last thing is to implement the estimate cost function. So once you're sure that A star is working with a heuristic of 0, and you're getting like all the correct solutions, then implement this estimate cost function. And so here it is. I've already written the if statements for you. So here, this is where you would compute and return the diagonal Manhattan distance. This is where you would compute and return the cardinal Manhattan distance. Here is where you would have your Pythagorean distance formula, and this one is already done for you. You don't change this one at all. Okay? So that is my recommended order in doing the assignment, and please remove those comments before you submit. And if you did not get any of the functionality of the assignment to work properly, please explain here in a comment. So just keep in mind that this assignment is pretty heavy on the creation and use of two-dimensional arrays in JavaScript. So if you are at all unfamiliar with 2D arrays in JavaScript, just like there's lots of YouTube tutorials on that. And not only that, but you can check, where am I doing this? I may put a D2L post about creating 2D arrays in JavaScript. One thing that I've seen, before everyone packs up, one thing that's not obvious about JavaScript is when you're creating a 2D array, one thing that some people have done is create the 1D array, right? Okay, so let me go back to the slides for this, actually. This will just take one more minute. Oh, Jesus. Okay. Okay. So what some people do is, in order to try and save time, they create the row, so they make that array, and then they put that array into another array y times. That sounds great. However, in JavaScript, you're not actually copying to a new array. You're inserting the same row y times. That means that once you've done that, if you put a value right here, it's copied to every row in that same position. So make sure that when you have your 2D array, you've done it in a way that does not do that. There are lots of different ways. There are one-liner functions using MapReduce. There's just a simple old for loop where you put things into an array. Whatever you do, just make sure that you're not doing that, because that has been the source of a lot of frustration. Okay, so that's assignment 2. Right before I'm done, let me go back here. You have an absurd amount of time. You have 3 full weeks to work on assignment 2. I know that you're busy, but please don't leave that until the last minute. The last minute is also kind of close to the exam, and the last minute is close to when I am going to be away. And so if you have questions, I'm getting back the day the assignment is due. So like, try and ask questions well in advance if possible. I'll still try and be on Discord. I'm going to a conference, not a vacation, so I'm still going to be working a bit, but just keep that